All right, let's talk about the secret sauce behind today's most powerful language models. It's not just about throwing more and more parameters at the problem, it's about a fundamental architectural shift, something called mixture of experts. This is how we're scaling AI intelligently. So let's dive in and see what's actually going on under the hood.
I mean, wow. That is a pretty bold statement, right? But it really gets to the heart of a huge problem we're facing. The dense model approach, the old way of doing things, is hitting a wall. It's just becoming totally unsustainable. So in this explainer, we're going to tear down the architecture of what's called mixture of experts, MoE for short, and see exactly how it's changing the game, letting us build and run models with 1 trillion parameters without melting our GPUs.
Okay, here's our game plan. First, we'll tackle the problem, the dense model bottleneck. Then we'll introduce the solution, the MoE architecture. We'll get into the weeds on the router's gating mechanism, see how that unlocks massive speed through sparsity, and finally, connect it all back to how we get trillion-parameter models on real-world hardware. All right, first up, the dense model bottleneck. You got to understand the problem to really appreciate the solution, right? Let's talk about this computational crisis.
So think about it like this. Imagine you have a world-class expert on, say, quantum physics, and you ask them, is the sky blue? In a dense model, that expert would have to read every single book in their entire library from cover to cover before giving you the answer. That's insane, right? But that's exactly what a dense model does. For every single token you process, the entire network, all of its billions of parameters, lights up and gets to work. This means your floating point operations, your flops, scale 1-to-1 with your parameter count. It's powerful, for sure, but it is just incredibly inefficient.
And this is where the two paths really diverge. A dense model, like we said, computes everything, every single time. An MoE model? Nope. It intelligently picks just a tiny, specialized subset of its parameters to do the job. It's not about working harder, it's about working smarter, a completely different philosophy.
So the big question is, how do you actually do that? How do you achieve that selective computation? Well, the answer is to break up the giant monolithic block and go modular. Enter the mixture of experts architecture. Okay, so if you look inside a standard transformer, you'll find these really critical layers called feed-forward networks, or FFNs. You can think of these as the computational workhorses of the model. This is where a lot of the heavy lifting, the knowledge recall, the actual thinking happens. And in a dense model, this FFN is just one massive single block of parameters.
Now, here's the genius of MoE. It takes that giant monolithic FFN and just breaks it apart. It replaces that one big block with two totally new things. A bunch of smaller parallel networks we call experts, and, this is the most important part, a lightweight decision maker called the router. So to put it simply, that's what mixture of experts is. You're swapping out one giant general-purpose layer for a whole pool of smaller, specialized expert networks. And then you have a router that acts like a traffic cop, figuring out which expert or experts to send the work to for any given input.
Okay, let's zoom in on that router. You'll also hear it called a gating network. This thing is really the brains of the whole operation. So how in the world does it know where to send each token? Yeah, this isn't random chance. The router is actually a small neural network itself. It's tiny, it's lightweight, and it has one job and one job only. During training, it learns to look at an incoming token and make a really smart prediction about which of the experts is the right one for the job.
And all of that complex decision-making comes down to this one surprisingly simple function. G of x equals softmax of w times x. Now, don't let the notation intimidate you. This is actually pretty straightforward. This formula is the engine that drives the whole MoE layer. Let's break down what each part does.
Okay, it's a three-step dance. First, the input token comes in. That's our x, which is just a vector of numbers. Next, we multiply that vector by a special weight matrix, w. Now, this matrix is trainable, which means the model learns the best values for it. The results of this multiplication is a list of raw scores, or logits, basically one score for each expert. A higher score means the router is more confident that expert is a good fit. And finally, we push those raw scores through a softmax function. All softmax does is turn that messy list of scores into a clean probability distribution, a nice set of percentages that add up to 100.
And that probability distribution, that is the key to the whole thing. Because with that in hand, the model can now enforce something called sparsity. And believe me, sparsity is the secret ingredient that makes MoE so incredibly efficient.
So take a look at this. This is basically what that softmax output looks like.
For any given token, the router has spit out a probability for every single expert in the layer. In this case, let's say we have 64 of them. And you can see it right there. A couple of these experts have really high scores. The router is screaming, use these ones. But most of them, they have tiny, almost zero probability. They're basically irrelevant for this specific token.
So what do we do with all these probabilities? We don't use all of them. Instead, we do something brutally efficient called top K routing. This is where the magic happens. We just look at all those scores and decide we're only going to activate the K experts with the highest probabilities. And K is almost always a tiny number. Think 2. Yeah, just 2.
Let's make this super concrete with a top 2 example, which is really common. The router looks at all 64 of those probabilities and finds the 2 highest ones. Easy enough. Then, and this is the critical step, it effectively sets the scores for the other 62 experts to 0. Poof, gone. They are completely ignored for this token. The token is then sent only to those 2 chosen experts to be processed. That means the other 97% of this entire layer just sits there, completely dormant, saving an absolutely enormous amount of compute.
And that technique, activating just a tiny sliver of the network at a time, is how we get to the mind-bending numbers you see with modern models. This is the real-world payoff for all that clever routing and sparsity.
Because of MoE, we can now build models that store a truly staggering amount of knowledge. We're talking 1 trillion parameters. That's the model's total capacity, its entire library of everything it knows.
But, and this is the punchline, thanks to that router and the top K sparsity trick, for any single word or token, it only needs to wake up a tiny fraction of that knowledge, maybe just 10 billion parameters. So you get a model with a trillion parameter brain, but the cost of thinking at any given moment is closer to that of a much, much smaller dense model. It's the best of both worlds.
So let's just quickly recap the big ideas here. First, old-school dense models are just brutally inefficient. They compute everything all of the time. Second, mixture of experts gets around this by using a smart router to pick and choose from a pool of specialized experts. And finally, top K sparsity is the specific trick that makes it all work, letting us scale to absurd sizes with manageable compute. Now, it's not a free lunch. You do have to deal with new challenges like load balancing to make sure some experts don't get lazy, but the trade-off is absolutely worth it.
You know, this whole architectural revolution has, in many ways, solved the problem of how to store vast amounts of knowledge in a model efficiently. That was a huge bottleneck. So that leaves us with a pretty fascinating question to chew on. Now that this problem is largely solved, what's the next great bottleneck standing in our way? What's the next big hurdle we have to clear to get to the next level of AI? Definitely something to think about.